today's topic, okay, whenever a gas is expanding, okay, just look at this, say, whenever the gas is expanding, no, we take a piston, cylinder, we enclose a gas, okay, again perfect gas, of course we are talking about perfect gases, and if the piston is going to be moved from this position to this position, okay, we call it expansion. And I can say that the gas molecules are pushing the piston. Don't think that I am pushing the piston, okay, no, the gas molecules themselves are undergoing expansion because of some changes, okay, and this expansion, right, is going to cause the piston to be displaced, okay. This is the displacement, I can call it delta x right now. This is the displacement of the piston, okay. So I can say that the piston has been pushed by the gases, okay. In other words, I can also say that the gases are applying force on the piston, and because of this force the piston is getting displaced. In other words, I can also say that the work is done by the gas, okay, work is done by the gas. I think you're clear with this, right? Because the piston is moving, okay, and obviously the gases are pushing the piston, okay. So today what we are going to do is we will look, okay, how much work is done by the gas while it is undergoing expansion, or even in compression also we'll see, okay. And we will take two cases, okay. Once we'll calculate for isothermal process, and once we'll calculate for adiabatic. There will be two formulas that we are going to derive today, okay. So basically the whole class will be based on these two. Once we have idea about these two topics, okay, we will not have a problem with the next topics, okay. So please pay attention. If you have doubts, you can talk to me, okay. So now see, this is a diagram, and this question can come for 3 marks, okay. That means they'll ask you find the expression for the work done by a gas during isothermal expansion. This is the first one we are going to start off today, okay. So see, if you have doubts, again I'm telling you, those students have not watched the previous videos, okay, you will have lots of doubts, okay. So do that first, okay. See okay, let me go back, let me start the derivation now. See, so this is the container. You can see we have gases here. How much gas we are going to take? Again, we are going to take 1 mole of a gas, okay. It can be any gas, but it has to be a perfect gas or ideal gas, okay. Now what is the area of this cylinder, okay? The area of this cylinder, the base cylinder, right, the base, okay, we are taking the area to be capital A. I think that is fine. So all this area here, also the area is A, even here the area is A, okay. Then I am saying that we are going to let this gas undergo expansion, okay. And how that expansion can take place, I can tell you, some amount of heat is added to the gas, because of which the gas is going to gain energy and will start pushing the piston, okay. So the piston will now be displaced from this position to this position, okay. So now I'm going to mark a region, okay, which shows the expansion or the increase of volume. Look at this, this is the region, right, or this space, right, indicates this is the amount of increase of volume, okay. The space represents increase of volume, okay. We can calculate that, that's not difficult at all, okay. Let me show you how much is the increase of volume right now. See, this, right, okay, this space here, okay, can be treated like a cylinder whose area is A, obviously the area is A, and whose height is dx, okay, yeah, whose height is dx. So what is the volume, guys, of this much portion, this portion here?
Sir, ADX.
ADX, okay. You take the area and multiply with dx. So guys, you tell me, does it represent the total volume of the gas, or this represents the increase of volume of the gas, guys? This area,
Increase in volume.
increase in volume. So I am going to call it dv, okay. In this case right now, I am imagining the volume to be not increased by a lot but a small amount, so I am writing dv, and the displacement of the piston is not lots, okay, it's only small amount of displacement, so I am calling it dx. I think this part is quite okay, okay, everybody can understand that much, okay. So now let me bring some of the terms now. See, you'll agree with me, the pressure of the volume of the gas, what do you think, guys, is changing or constant? Constant or changing, guys? Pressure changing, okay. What about the volume? Obviously volume is also changing, okay. So let me say that P and V, okay, they represent the pressure of this gas, the force applied by this gas per unit area, that is the pressure, and the volume of the gas, okay, V, okay, these are the two values at any instant of time, okay, at any time. at any instance, okay, instance of time. That means suppose you ask me what is the pressure right now, I can just simply call you, let's say it is P. What is the volume right now as it undergoes expansion? Let's call it V, okay. Now I also have to tell you, okay, the entire expansion right now, okay, the piston which has been pushed, okay, indicates expansion. This entire expansion, I'm telling you, happens at constant temperature. That means the temperature is not going to change, okay. So that is the property, right, of isothermal expansion, and that is what is this topic is all about, okay. Okay, so check now, okay. So what we are going to do next is check, okay. It's going to be simple, don't worry, it's fine, but let me tell you what is going to happen, okay. Say we are going to start with the initial volume of V1, and the gas will finally reach to a total volume of V2. V2 represents the final volume, V1 represents initial volume, okay. And when the initial volume was V1, I'm saying that at that moment the pressure is P1, okay. And when the final volume is V2, I'm saying that the pressure is P2 after expansion, okay. These values are. Then of course it is isothermal, so I'm saying T is constant, okay. I'll send you these notes so you can go through. And of course I told you, right, P and V of course will represent pressure and volume at any time in between, also in the initial position, also any time you want to talk about, you can just use P and V as well, okay. So look at this now. Say we know at any time, right, at any instant of time, at any time, the pressure of the gas can be defined as force per unit area. So I can also write the force applied by the gas at any time will be equal to pressure at that time into the area, okay. So this is, of course, we can use anytime we want, okay. Now don't forget we are talking about work done. If you remember that is our topic. So how much is the work done by the gas, okay, during expansion, okay. So that is what we're going to calculate, okay. But let me show you a graph, okay, that will tell us everything about what is going on. So let me just show you that, and then I think we can proceed properly, okay. See, if you have doubts again, you can talk to me directly, okay. See, so this graph is what we have right now. See, okay, try to understand everything of it again. It is a pressure volume graph. So this is pressure axis, this is volume axis. If I'm going to the right, I'm talking about more and more volume. If I'm going up, I'm talking about more and more pressure, okay. If you remember, I told you our gas starts from a state A, let's call it A, where the pressure is P1 and the volume is V1, okay. So this is our starting state, okay. And what we are doing, we are letting this gas to expand, okay. So when I let this gas expand, see what will happen, okay. The volume now that I'll get finally, okay, slowly it is expanding. So now we reach a volume called what, V2, and now the pressure is P2. You can see the values also here. The value of the volume is V2. I hope so you can see that, whichever I'm marking. And the volume initially is V1, so this is the final volume, and initial pressure is P1 and final pressure is P2, okay. Now look at this, okay. See, if I ask you, okay, how do you calculate work done? What is the answer, guys? How do you calculate work done by anything?
Force into distance.
Force into distance or displacement.
Dot product of force and
Okay,
displacement.
dot product also. But in this case, I don't have to talk about dot product. I can just directly go, okay, because direction of force and displacement will be same, okay. So the cos will be 0 degree in this case, okay. So check now. Say, so work done, you told me just now, is force into distance or displacement, okay. But you have to agree with me, okay. You can apply this formula only if what? Only if force is what? Force is a constant. I cannot apply this if during our displacement the force is changing. I cannot apply this, okay. I'm repeating again, we cannot apply this if force is not a constant, okay. Only I can apply if the force is constant. Now think, okay. Do you agree with me, right? If I take the gas from pressure P1 till I reach to a pressure P2, okay, tell me the force applied by the gas will remain constant or not a constant? The pressure
So
is
not a constant.
so from which volume to which volume? Starting from volume 1 to which volume?
To
Starting
V2.
to V2, right? The pressure is constant or not a constant? It's not a constant. Okay, during from expansion from V1 to V2, pressure is not a constant. That means I cannot apply this formula, because if pressure is not a constant, then force also is not a constant. The force is going to continuously change, okay. But check whether you agree or not. Okay, please look at this. Okay, look at my graph now. See, look at this. Okay, what is this? What do you think is this, guys, from here to here? Does it represent a total change of volume, or does it represent a very small change of volume?
Small change.
Small change
Very
of
small
volume.
change.
Okay, if it's a very small change in volume, okay, what do you have to say about the pressure, guys? Do you think for a very small change of volume, can I imagine the pressure to be constant or not?
Yes, sir.
Okay, I cannot do it from volume 1 to volume 2. Definitely the pressure is changing. Okay, from here to here. See, pressure is changing from P1 to P2 for volume V1 to V2. Okay, but for a very small change of volume, which is here right now, okay, I can tell you that the pressure is constant. I can show you in the graph. What do I mean by that? See, this line here, okay, check this line here, okay, check this red line that I've drawn. Let me make it black, I think. Okay, black line, let me take, see this black line. Okay, the black line from here to here, what do you think it represents, guys? Does it represent pressure or pressure at any time? Pressure at any time, actually, right? Okay, I could have drawn it over here also. That represents pressure at that time, later time. Okay, but right now this black line that I'm drawing, right, it's a long line. It is in the vertical direction, so it represents the value of what? It represents the value of pressure. Okay, now check, do you agree that, okay, after a volume of dV, okay, this is the volume dV, right, this black arrow, okay, can I imagine it to be almost same as the first black arrow or not? Just check, almost same or different, these two black arrows?
Almost same.
Almost same. Okay, that is what I meant to say. Okay, that means for a very small change of volume, I can imagine the pressure to be constant. Okay, let's calculate how much work is done during this small expansion. Okay, so let's do that first. I cannot do it for the entire case directly, okay, because the force doesn't remain constant. Okay, but let's say for a very small expansion, how much expansion we are talking about, guys? dV. Okay, for a very small expansion dV, tell me what is the work done. Will I call it W or dW? dW, very small amount of work done, dW. Okay, definition is what? You have to say force into displacement, and the displacement is what, guys? Is it very large or small displacement? Very
Small.
because it is a small expansion, so the displacement of the piston will be very small. So I'll call it not X, I'll call it dx. I think you are clear with this part. What is dw, I think, is clear. I think what is f, it is clear. Okay, and what is dx is also clear. Okay, now let me bring it back what I wrote earlier. Okay, pressure is anytime is equal to force by area. So force can be replaced by what? Pressure at that time into area. I'm going to do that right now. Okay, so check. So your dw is equal to what, guys? Pressure into area into dx. I think it makes sense, right? See, because in place of force, I'm going to write pressure into area. So I've done that, pressure into area. Okay, so dw can be written, small amount of work can be written is equal to what now, guys? Tell me, what is this? P, and what is ADX? You have already told me earlier. Let me show you, remind you again. Say,
So
what is
volume.
it is volume or very small increase of volume?
Small.
Increase of volume. Okay, that is what I told you earlier, right? A very small amount of increase of volume dV, we can get it by writing A into dx. Okay, so that is what I'm going to do right now. Okay, where have I written? It's here, no? So I'm going to do that. Okay, so in place of A dx, right, it represents a small increase of volume. That means nothing but P into dV. So I think you are clear what is this, right? Now we have very nice things to talk about. Say, this is pressure, this is volume, which makes sense for us, and both of them are there in our graph. Okay, we have pressure also and volume also. Let me show you, go back to the graph and let me show you now. See, okay, do you agree, right? This is like dV, right? The dV is like the length. You can just check that dV is like the length from here to here. Let me show you with blue, from here to here. This is dV, and from here to here it is what, guys? It's like breadth, it's like pressure, no? Do you agree with that? Let me use green now. Okay, from here to here it is volume, and from here to here it is like pressure. It's like PdV. Okay, so when I multiply in this graph, okay, look at this and tell me, if I'm multiplying green line, which is P, and this green line, which is dV, right? Do you agree with me that I'm going to get a small area in this graph or not when I multiply PdV in the graph?
Yes, sir.
Yes, sir.
It's like a rectangle there. Okay, so when I multiply this, say I multiply P, which is this line, and dV, which is this line, I'm going to get this area of this rectangle. Okay, so what do I mean by that? Let me show you. Say, So indirectly, if you are calculating area, okay, if you are calculating what, guys? Area in the graph, that means indirectly you are calculating what?
Work done.
Work done. Okay, can you understand? Did I make sense?
So that is not a triangle, no sir.
That is not a triangle. So why did you say triangle?
You said
I said triangle.
yes, sir.
Rectangle.
Rectangle. I said rectangle. Okay. Jansika.
Okay, sir. Okay.
Yes. Okay, not triangle. Okay, so see, this is your P line that I drew. This is your dV line. Okay, small change of volume. I told you, right? If I multiply these two, right? Actually, what am I going to get? I'm going to get this area, right? But if you look at this
Yes,
formula,
sir.
okay. But if you look at this formula, right? What is representing? P dV represents what? Obviously, it represents area in the graph, but it also represents what?
Yes, sir.
Small amount of work done.
Small amount of work done. Okay, so now you tell me, are you clear with this, all of you? Just check. After that is very simple. After that's not a problem. So guys, do you understand this area that I've shaded here? What does it represent, guys? Just tell me that.
Small work done.
Small work done, very good, during the expansion of a gas from by a small volume, okay, at a particular value of pressure. Okay, now think, okay, can I do this and can I calculate another rectangle here or not? Area of this rectangle here, yes or no?
Yes, sir.
What will that represent? That will represent work done or or small amount of work done again.
Small amount of work done.
Okay, do you agree with me? I can do it for the entire curve or not, like this? Just check, guys. See, but for all of them, okay, but for all of them, what do you think? I'm going to take the same pressure or different pressure I have to take? Different pressure. See, for all these blocks, no, I have to take different pressure. If I've calculated all of this work done, okay, all of these small boxes, if I do that, if I add all these small boxes, now tell me, will I get the work done or total work done?
Total work done.
Total work done. That is what we are looking for. So I'm going to show you very quickly. Okay, so I hope you understood this part. So I'm going to go back here and write down all the things needed. Okay, so you are clear with what is this, right? dW is force into displacement. dW is equal to pressure into area into dx. Then I wrote dW is equal to pressure into dV. Okay, now if I just add all of these dW, that means all of these small rectangles that I have, okay, for the entire curve or under the curve, okay, I'm going to get the total area, which is shaded by yellow color. Okay, the total work done. Okay, this represents total work done. See, net work done I've written here. Okay, so that is what we are going to calculate. Okay, and the method, I don't know whether you are okay or not with this thing till now, but how do we do, guys? What do we do to calculate the total area under a graph? Which method do we use?
Integration.
We use what?
Integration.
Integration.
Method.
Yes. Okay, if I'm trying to add small things, right, indirectly we are going to say that, yeah, we are talking about integration. Okay, so we are going to integrate now, integrate this dW, that means add up all the small work done, and I'm going to get the total work done. Okay, so the way to represent this is give this sign, right? The symbol is this. Okay, and I have to tell you, okay, from which volume to which volume we are going, right? So we are going to start from volume V1 and we stop at volume V2. Okay, lower limit and upper limit. Okay, also if the volume is V1, okay, tell me how much work is done by the gas.
0.
I've already written. Okay, but can you understand, guys? Because when the volume is V1, it is initial volume, we just started, the piston has not been pushed, that means the corresponding work done is also how much by the gas, guys? 0. Okay, when we have stopped, okay, when the piston has stopped at a volume called V2, do you agree with me that the gas has pushed the piston or not?
Yes, sir.
So the corresponding amount of work done, will I call it W or dW, or what will I call it now, guys?
W.
I'll call it W, not dW anymore, because now it represents small work done or total work done? Total work done. Okay, so now I think we are almost done. Okay, see, we just have to integrate this part. Okay, now before I proceed, I have to tell you now what is the integration of left hand side. See, integration of dx is how much, guys? Who knows this one? Integration of dx, don't forget, it is equal to x. If you add all the small x, then you get the total x or not? So you get x. Okay, if I have limits from 0 to, let's say, capital X, then my answer will be equal to capital X. Okay, I don't have to talk about this. I can directly use for the time being. You also remember this integration of dw. Now tell me guys, what will I get? What do you think? I'll get w, or
So W.
I'll get w. Integration of a small work done, I'll get total work done. Integration means add up, okay? Total work that I'm going to get. So my left hand side has limits from 0 to w, so I have to put this line here. I think you know, I have to write here lower limit, I have to write upper limit, I have to put here upper limit, I have to put a lower limit. But don't worry, this is very simple. I'm directly going to get w minus 0. Okay, so my answer is going to be w. Okay, so I'm not going to confuse you here much. Just remember the integration of work done I'm going to get is w. Okay, equals to, look at this right hand side now. Okay, look at this right hand side and tell me, is your p a constant or not a constant?
Constant.
For dv, right, your p is constant.
Constant.
But from a volume of v1 till we reach which volume, guys? v2.
V2.
Your p is constant or not a constant?
Not a constant.
Not a constant. It changes. Okay, and you will agree with me. Okay, I can show you how it changes. Okay, can you tell me how it changes, guys? Okay, how it changes, tell me. Can I write PV equals to nRT? I can use this, right? I told you I can use this for any ideal gas anytime I want. I can use this.
So as volume increases, pressure
Yes.
decreases.
So how does it changes with volume? Look at this. Pressure equals to nRT by volume. I think you'll agree with me, right? This is how the pressure changes when the volume changes, right? Can I use this or not? Provided it is what process? It is isothermal process. Okay, otherwise there should be a power gamma. Okay, but this is not the formula, of course. Okay, but I think you understood what I'm trying to say. Okay, so now tell me, guys. Okay, can I do this substitution or not here? Allowed or not allowed? At any point of time, my pressure can be written as n into r into t by what, guys? Volume at that moment, and then I can write dv. I think this part is clear. Just check, guys. In place
Yes,
of p,
sir.
I'm writing this. Okay, and because our number of mole is 1, so I can just remove that n from there. No, n is equal to 1. Okay, so now let's just proceed and solve it. Now tell me, looking at this formula, now tell me, okay, which are the things which are constant inside the integration? Is r a constant or not?
Yes, sir.
Yes, r
Yes,
is a
sir.
universal gas constant. You'll also agree with me the temperature for this isothermal process is also constant.
Constant.
What is not constant is what? Is that volume constant or not a constant?
Not a constant.
Not a constant, because this volume is going to change. Okay, yes, Giovanna, I'm recording. Yes, those who have bad network and all. Okay, nope, no other option I have to record only. Okay, but some students, they really become lazy, huh? Sometimes they don't join. No, today also so less students. Before I used to have 40 students, 35 students joining. Now it has reduced. Okay, now see. What about other tuitions? Other tuitions you are going continuously, regularly?
No, sir, my chemistry tutor is not in Shillong, so he's on vacation.
Okay, what about other okay, maths and all other students? You're having continuously your classes? Yes. Okay, you don't want to say. Okay, we'll talk later. Okay, about that. Okay, see. So yeah, now you know what? This is what I need to integrate now. And I told you, okay, these things you are going to learn better, okay, or properly in class 12. Okay, in class 11, okay, this is the most worst thing to do, okay, for me. Okay, try to explain this, but no point. Okay, you won't understand fully. Okay, so what we do is basically we just use the formulas directly. Okay, so right now also I'm going to do the same thing. Say, whenever you see integration of dx, but I have divided by x, please remember this. Okay, whenever I see integration of dx and divided by x, the variable itself, your answer should be log x to the base e. Now I want to know, okay, have you ever come across log function? Have you ever used before? Have you heard about them at least? This is a formula, huh? I'm writing it here, see. So you don't ask me from where it is coming. Okay, just remember for the timing. Class 11, I'm so sorry. Okay, what to do? Okay, but remember that integration of dx, but I have divided by x. The answer comes out to be what, guys? Log x to the base e. Is it okay? Can I use this directly? I have given you so many other formulas also. Let me remind you. Integration of x to the power n dx is how much, guys? X to the power n plus 1
plus 1 by n plus
n
1.
plus 1. Okay, this is one of the formula I've given you, yes. But today I'm giving another formula, okay? Okay, now what is log? If you want to understand what is log, I'll just tell you that. But let me tell you what is E first here. E represents a number which is around 2.7 something something something. Okay, so E is that number, and this log, okay, you'll also see in your calculators are there. Okay, now I'll just quickly show you what is the meaning of taking log. Okay, and then I'll come back to my original formula. See, okay, tell me guys. Okay, see, what is the power? Yeah, 2 to the power 5 is how much?
32.
32. Okay, 2 to the power 4 is how much? 16.
16.
Okay, very easy question. Now I'll ask you like this. Okay, log of 32 to the base 2. If I'm writing like that, if I write like this, it means I'm asking you, okay, what is the power of 2 so that you get 32? And your answer is
5.
5. So if I take log, right, if I'm writing log, it indirectly represents that I'm asking you, okay, what is the power of this number here? Base, we call it base. Okay, what is the power of 2? Okay, Prayas is also joining after half an hour. What is the power of this base so that you get an answer which is this one, which is 32? And your answer is what, guys? 5. So what is 5 actually represent, guys? It represents what? Power. Okay, power of the base. Yeah, power of the base. And that's what log function is all about. Okay, log means knowing the powers. I'll give you another example. See, if I write log and then I write here 100 and then I write here base 10, what is the answer, guys?
So 2.
Yeah, the question is, what is the power of 10 so that you get how much? 100, right? And your answer is 2. Are you clear, guys? Little bit at least with log functions. Little bit at least, if it is okay.
Yes, sir.
Yes, sir.
Okay, I think basic idea is clear what is log. Okay, let me come back. Okay, now see, so same thing is going to happen now. Okay, I'm going to use this and I'm going to use log, but this time check. Okay, every time you integrate, right, you're not going to get any random base. Okay, you're going to get a base which is E, I told you, which is a value of around 2.7 something. Okay, we call it natural log also. So let me just expand integrate this one now. Okay, so please guys help me out. I'm going to write here RT. Okay, now you tell me, do you agree with me? It looks like dx divided by x or not? The integration part, it looks like
Yes, sir.
dx by x. It looks like dv by v. Okay, so what is your answer, guys? Your answer should be
Log.
log
E. V.
log ev. Okay, how to read it? Log v to the base e. Can you understand, guys, from this step to this step? Is it okay? Can I say it's okay? Just check. It's okay, no? You said okay, no? Yes, waiting for some response. Then I think I can
Yes,
proceed
sir.
peacefully. I can proceed. Yes, waiting. Some more response. Okay, Parthif is saying yes. Okay, then we'll proceed. Okay, say. So check now. Okay. Now I have written the integration of dx by x or dv by v, that is your log v to the base e, but I also have to write the limits, right? The lower limit and upper limit. And how do we do it after integration? We put a bar like this. I must write here lower limit and I must write here upper limit. So that is what I've done. Okay, now I'm going to put the upper limit and lower limit. I'm going to put the upper limit first and then I'm going to put the lower limit in place of v, because these are the values of volume. Okay, so I'm going to write check w equals to, okay, rt log of, what should I write, guys? I should write v or v2 now.
So V2.
V2 upper limit I've put, base e only, minus, what should I write? Log again,
Log.
but this
V1
time I should write here
is E.
v1. Okay, I think this part is clear. Can I say this, guys? Is clear? Check.
Yes, sir.
Okay,
Yes.
check. Anybody did not understand, please let me know. Okay, so now tell me, w is equal to what? See, okay, one more thing you have to understand, huh? If I have log of, let's say, 10, if I write here let's say I write here 5, okay, then I write here minus log again, okay, I write here 3 and then base what? 10. Okay, the answer for this is this. Okay, whenever I have, okay, I should not have written 3 here, 5 or 3 doesn't matter actually, it can be any number here. Okay, let me just call it x and y. Whenever you see we have this thing happening, okay, log of x, log of y, but I have a minus sign in between them. Okay, this is what you need to do. See, you will write log, because both of them have 10 as the base. Okay, same base, you are going to write 10, and this x and y you are going to divide. So x by y. Can you understand, guys, what I did just now? This is how your log functions are solved, or let's say simplified. Did you understand, guys? If I have a minus, what do I need to do? Okay, I'll show you again. If I have log to the base e, I have x. I have minus log to the base e, okay, and we have y. What is the next step, guys? How can I simplify? I can write log
Log
to the base e
x
x
by y.
by y. Yeah, this is what I can do with log functions. Okay, so that is what I'm going to do right now. So you tell me, what can I do with these two, guys? Tell me, what do I write? Log to the base e. I'm going to write what, guys?
V2 by
v2
V1.
by v1. Correct.
Or
Okay,
v2
so
by v1.
yeah, so actually we got it what we wanted to calculate. So now please read and tell me, what is this w? Properly, if you can tell me, I'll be very happy. This w, think and tell me, huh?
Total work done.
Very good. Total work done. Total work done by whom?
Gas.
By a gas. Any type of gas or perfect gas?
Yes.
Perfect gas.
Perfect gas on ideal gas. Yes, ideal gas. Don't stop, don't stop, continue. When the gas is undergoing, when the gas is,
Expansion.
very good, when the gas is undergoing expansion,
Isothermal expansion.
from which volume? V1 volume to which volume?
V1 to V2.
Under what kind of conditions? Under any conditions or under isothermal conditions?
Under isothermal
Isothermal
Under
conditions.
isothermal conditions. And do you agree with me that the temperature also plays a role in the work done or not? Check. Yes or no? What does
Yes,
it
sir.
mean? The gas will do more work if the gas is at lower temperature or higher temperature.
Higher
at
temperature.
higher
That
temperature.
is what it means. If the gas is undergoing expansion but at a very high temperature, it is going to do a lot of work while pushing the piston. Okay, and obviously, right, V2 by V1, don't worry about this. This is quite all right. V2 by V1, we are going to get positive. Okay, let me tell you like this. V2 by this entire thing, log of V2 by V1, I'm going to get what, guys? Positive if V2 is greater than what? V1, numerator
V1.
greater than new denominator, and this thing only I'm going to get negative. Okay, if V2 is less than what? V1. So now you tell me, okay, what does this represent? Expansion or compression?
Expansion.
So
Expansion. So you
expansion.
expect a positive, okay, during expansion, and V2 less than V1 means what?
Compression.
Compression. So what kind of sign do you expect for that log?
Negative.
Negative. You can see that from here also, right? V2 greater than V1. So I'm going to get what, guys, here? Positive. And if V1 greater than V2, it is compression. Okay, so I'm going to get what sign, guys? I'm going to get a
Negative.
negative sign. Okay, so I can get positive and I can get negative. I will talk about that also in detail. Okay, but let me just work out with one more step here. Okay, obviously I told you we can use this, but there's one more step after this. Okay, see, so check. That step is this. See, I don't want to write log to the base e. Okay, I want to change it to log to the base 10. Do you understand what I did just now, guys? Instead of which base? Base e, I want to change it to which base, guys?
10.
Base 10. We can do that, okay, provided I do this. Check how it is done. I'm just going to show you one step. Okay, we have to come and multiply by a number called 2.303. So suddenly if you see this, you be sure that we have changed the base from what base? From a base e, we have reached
From
which
base
base?
E.
Base e to base 10, but we have to multiply
10.
with that number. Okay, so now that is the step I'm going to do here. See, so w equals to how much, guys? I'll write 2.303. I'm going to write RT. Okay, and then I'm going to write what, guys? Log or log to the base 10? Log to the
Base
base 10 and V2 by what? V2 by V1. Is it okay, guys, what I did just now? Check, check, check. Yes or no?
Yes, sir.
Yes, sir.
Okay,
Yes.
okay. So this is fine. Okay, now can you please repeat? Okay, Aisha is not okay with that. Okay, so Aisha, can I ask you exactly from which part? This part. Are you asking me this part? Okay, see. So what we have done, you know what? See, I want to ask you, okay, what is the meaning of log x to the base e? That means I'm asking you, what is the power of e, so that I get what? I get x. E to the power, right? E to some power, okay? E to the power, right? I get equal to how much? X. I'm asking you what is this power, and that is the meaning of writing this, right? Writing this means I'm asking you what is the power. Power of whom? Power of e. So that when I give that power to e, I get equal to how much? X. Okay, that is what actually I'm asking you. Okay, so I can ask you another way also. Okay, what is the power of 10, so that I get the same number as what? X. Okay, okay, power of e also will give me x. Power of 10 also can give me what? X. Okay, and this entire thing means what is the power of 10, so that I get x. Okay, and you know what, it is found that this value, right, when we express in terms of base 10, is found to be equal to what? Log of x to the base e divided by 2.303. So the values are related with this equation. Can you understand what I said just now? See, you can find the value of log of x to the base e. You get some answers, okay? But you can also express the power of 10, power of 10, which will give you again x, okay? And that is found to be equal to what? Take the log of x of this to the base e, but you divide by this number and you get back this one, okay? So this number, just remember, whenever I want to change, I want to replace log x to the base e with a log of x to the base 10, okay, from e to base 10, okay, then you have to multiply by this number called what? 2.303. So don't write here, you can write over there, okay? That is the step I've done here. See, because here what do I have? I have a base of what? E. But now check, my formula has a base of 10, and I have changed from e base to a 10 base because the values are related by this factor, which is your 2.303. okay, right now I don't have this, we cannot just go and prove this one right now, okay? That is going to be exactly too much actually for right now for us, okay? Just remember the step, that is going to, I think, should be fine, okay? Later you can just use your calculators also, okay, so check how they are calculated, okay? Guys, can I say this part till is okay till now?
Yes, sir.
Okay, so suppose, okay, yeah, so now suppose, okay, I don't want to express the answer, okay, when the volume is changing from V1 to V2, okay, but I want to bring P1 and P2. Pressure is changing, volume is changing, and P1, P2 are corresponding to V1, V2. Check how we can achieve that, okay? So see, I am going to write P1, V1, right? Do you agree it is a constant?
Yes, sir.
Okay, it is isothermal, no? So P1, V1 is a constant, we know this. Even what is constant, guys? P2, V2 is a constant, okay? Are they different constant or same constant? What do you think, guys? P1,
Same constant.
same constant, very good.
Same.
That means what? P1, V1 is equal to what?
P2,
V2. That means, you know what, I also can write what? V2 by V1 can be written as what, guys? P1 by P2 from this formula, okay? So in place of this, now check, I can write work done by a gas during isothermal expansion equals to 2.303. I can write RT for 1 mole of a gas, otherwise there will be N there in front, okay? Then we can write here log to the base 10, but this time I'm going to write what, guys? P1 by P2. So if I tell you the volume has changed from V1 to V2, use this formula. If I tell you, okay, the pressure has changed from P1 to P2, use this formula, okay? And you get the same thing. You don't get a different answer, you will get the same answer, okay? It's not going to be different, okay? So guys, can I say that you have learned what I did just now? See, this is the formula that we have got. So that is this work done, right? Okay, that whatever we have got actually also represents what, guys? Whole, it represents area or whole area under the graph.
Total work done.
Total work done, it represents the whole area under the graph, okay? So we have got that formula right now. Let me write it once more, okay? So W equals to how much we got? 2.303. I'm going to write RT, and I'm going to log to the base 10, okay, V2 by V1, okay? Don't forget, I told you again and again, okay, this can be asked for numericals, it can be asked for derivation, and obviously we are going to use for the next topic next day, okay? So guys, can I say it's okay? After you say it's okay, then only I can proceed to the next topic.
Yes, sir.
Okay.
Yes, sir.
Oh, one more thing.
Yes,
One more
Yes,
thing.
sir.
Yeah, one more thing. Okay, fine. You said yes. Okay. Oh, one more thing. Okay, one more thing. Say. Okay, check. You have to tell me what is going on. Huh? Say. Very nice concept it is. Okay. Say. So these are the gases. The piston has reached here. Okay, from here to here. Okay. You know what is this called? This is called expansion. Everybody is clear. So tell me, V2 is greater or V1 is greater? Initial or final volume is greater?
Final.
Final volume is greater. Yes. Okay. What kind of W I'm going to get? Positive or negative?
Positive.
Positive. Final volume is greater. Yes, positive. Okay. Positive work done means, okay, this work done by the gas, it is positive. Okay. And you know what it means? It means that the piston is really pushed by the gas. The piston is really pushed by the gas. That is the meaning of work done positive. Okay. But if I do the same thing but opposite way, see, I took a gas, okay, and I saw that the piston is not here but the piston is reached here now. Okay, now you tell me, V2 is greater or V1 is greater?
V1 is greater.
Initial volume is greater but your final volume is less. Now the gas is only occupying this much space. Now you tell me, okay, what kind of work done am I going to get if I use that formula? Positive or negative?
Negative.
Negative. Okay, so I am going to say work done by the gas now this time is what? It is?
Work done by piston.
Yes, yes, but wait a minute. But what will I call it? Will I call it work done by the gas positive or negative?
Negative work.
Okay, you have to read it like this, huh? Work done by whom? By gas. It is found to be what in this case? Negative. And it
Negative.
represents what? You know, it represents as if not the gas is pushing the piston, but piston is pushing the what?
Gas.
Okay, but I have to read it how, guys? I have to call it work done by the gas. And I have to say it is what? It is negative. But indirectly what it represents, guys? It means gas is pushed by whom?
Piston.
Piston.
By the piston.
Gas is pushed by the piston. Are you clear with this idea, guys? Just check. I have to read it work done by the gas, and if it is found to be negative, it represents that the gas is pushed by the piston. Piston is gas is not pushing the piston, but piston is pushing the gas. Okay, that's what it represents. But I have to speak like this. I think you got my point.
Yes, sir.
Okay, and suppose, okay, if I tell you work done in this case, work done by piston, what is your answer, guys? Tell me, will it be positive or negative?
So positive work.
Work done by piston will be positive, but work done by gas will be negative. Okay, and what about here, guys? Work done by piston, positive or negative?
Negative.
Work done by piston, yes, in this case it will be not zero. Why I'm writing zero? It is going to be negative. But I think you got my point, what I'm trying to say, right?
Yes, sir.
Okay, then I think we can proceed. Okay, so the first derivation, I'm sure you are clear. The second derivation is exactly a copy of this. Okay, but of course few small changes are there. I'll send you all these notes, please. You have to study it today only. Okay, then numericals, two numericals you have to do based on these two formulas. Okay, now say I'm doing the same thing, but this time I'm going to calculate. Okay, work done again by the same gas. Okay, but now this will be under adiabatic conditions. So you are going to say, right, that we will take the gas again, we will let the gas expand, okay, and the piston will again reach some position, okay, where will I have a new volume of how much? We'll start with P1 volume, we'll start with V1 volume, P1 pressure, then we'll reach a state of how much pressure, guys? P2, and we'll reach a volume of V2, okay, no, same thing, but this time temperature is not constant. Okay, and we have learned something, right? Under adiabatic conditions, right, do you gain heat or you don't gain heat? Delta Q. You don't gain heat, you don't lose heat. Okay, so what happens to the gas? The temperature remains constant, or during expansion the temperature falls?
False.
Temperature falls.
Temperature falls. So P1 V1 is a state with a temperature of how much? T1, higher temperature, okay, and P2 V2 is a state which is after expansion, so the temperature is going to be T2, and T2 is higher or lower, guys? It is
Lower.
lower temperature. Okay, but we know one more thing about adiabatic, right? And I'm going to use that right now. Tell me, what is that, guys? I can write P and V is equal to constant, or product is constant, or this is wrong?
So it's
PV
wrong
This
as
is not wrong,
temperature is
right?
not
Right?
same.
We should write what, guys? PV to the power gamma can be written as constant. This is allowed. Okay, this is we can do. Yes or no, guys? Check. This is what I'm going to use right now. Okay, and that constant I'm going to use as k right now. See, p v to the power gamma. Let's call it just k for the time being. Okay, I'm going to use it. So let me show you how to use it. Okay, see, I'm going to write p1 v1 to the power gamma is equal to k, a constant. Product is constant, and the product later also, right? p2 v2 to the power gamma will be equal to same constant k. That means I can write here p1, p2 v2 to the power gamma is same. Okay, this is what I can use. Okay, so let's come back to the derivation now. See, I don't have to teach you half of the things because you already know this one. Agree with this one, right? Check. Work done of the by the gas, right, will be equal to how much, guys? Pressure into dV. Again, I'm doing for the small work done, right? Same thing. Okay, small work done. We cannot directly go for big work done because the pressure or the force doesn't remain constant. Okay, so again I'm going to follow this method, and you know what I'm going to do next, right? What I'm going to do, guys, next? Integrate to calculate the total work done. Same things. This still here it is same. Okay, but let me show you the graph. See, when you come back to the graph, right? Okay, I think you can already understand. Before we had a graph which was this, a very slow decrease in pressure, but now I'm showing you a very quick decrease in pressure. Okay, so this is your adiabatic expansion. Okay, again for a very small volume, this one, see guys, for a very small volume, this one, let me use red, very small volume. Okay, I can imagine the pressure to be constant, and this is the value of the pressure at that point, and I can imagine the same value somewhere here like this. Okay, so when I complete this rectangle, okay, complete this rectangle, this area which I'm shading, right, is nothing but what, guys? It's a product of P and what? It is product of P and dV. So I have to calculate the entire area. So that is what I'm going to do now. Okay, can you automatically tell or already tell me, guys, what do you think? I'm going to get the same area like before or much smaller area compared to isothermal? Before the graphs were like this, before the graph was like this, now the graph is like this. So I'm going to get, yes, very good. Okay, I'm going to get smaller area. That means work done during which process? Adiabatic process will be smaller, right, compared to isothermal. Okay, that is what we are going to do now. Okay, see, I think you are clear with this part, because now we need to integrate from volume V1 to volume V2, same process, 0 to W, right? Okay, but check. Okay, this is what is true for adiabatic change. P v to the power gamma is a constant. Okay, where gamma is, I've defined to you before also, I've written here again, so you can do that. So we are going to use these things now. Say, earlier I wrote PV equals to nRT. I wrote P equals to nRT by V, but this time I cannot do this. Okay, I cannot do this because pressure does not depend on inversely on volume, but pressure depends inversely on the volume but to the power gamma, right? This is what we have done, right? I've written just now PV to the power gamma is a constant, so I can write pressure is equal to what? Constant by volume to the power gamma. This is what I'm going to replace in place of your pressure. Earlier I have replaced pressure with this one for your isothermal expansion, volume to the power 1. Okay, this is we have done before. Now we are going to replace this in this formula. Okay, so let me do it and let's check whether it is clear or not. Okay, see, I'm going to do it here fresh. You can check the notes. If you have doubts, please ask me. Okay, see, so dw equals to, okay, integration from 0 to w equals to, let me write again, p dv from a volume v1 to a volume v2. And just now I told you, right, from a volume v1 to v2 the pressure does not remain constant, but the pressure depends inversely on the volume with a power gamma. So I'm going to replace that right now. Okay, so check left hand side. Can you tell me directly now, guys? I think you are okay with this. How much should I write? I can write directly equal to W. Yes, very good. Okay, pressure is not a constant, will be inside, so I can write how the pressure changes with volume, and that is this K by volume to the power gamma. Gamma is a constant, that is all right. Okay, now you tell me, can I take the K outside or not, guys?
Yes, sir.
Yes, K is outside,
Yes,
so I can write V1, V2, then I can write dV to the power V to the power gamma. Okay, now we need to integrate this part. Say, integrate this part. So how to do it? Say, earlier it was like this. I wrote dV by V integration. I told you the answer is log to the base E, right, for V, right? This is what we wrote earlier. Okay, but now I have a power 1 or I have a power gamma. We have a power gamma. So I cannot use this formula. This is only when the power of V is 1. Okay, please remember this. Again, explanation I'm not doing it. I'm just telling you which formula to use. So power 1, yes, you can use this, but for any other power you cannot use this. Okay, so what formula do I need to use? See, I'm going to write like this: W equals to K integration from V1 to V2 volume to the power minus gamma dV. I think you're clear with this. Just check. I've taken the volume from denominator to numerator, right? So it will have gamma power or minus gamma power now.
Minus gamma.
I've just taken it above. Okay, so it is minus gamma power. I'm going to apply this formula now. Okay, please check. Integration of x to the power n, okay, which is not equal to minus 1. Okay, then you have to write dx equals to, you know what is the formula is. Okay, again, can you tell me? X to the power
X n plus
n plus 1 divided by n plus 1. I am going to use, yes, okay, I'm going to use over here. So please apply. I'm waiting, equals to K. I'm writing again. So let's integrate this part. Say this whole thing will become or reduce to this. Okay, now this one on the right hand side. So in place of x, what should I write, guys? I should write x or I should write v? V. There we have x changing, here we have volume changing. So v to the power
Minus gamma plus
n plus 1. What is the power here, guys? Here the power is n, but here the power is n or minus gamma.
Minus gamma.
So in place of n, I'm going to write minus gamma. Then I should write plus 1. Plus 1, that means I must increase the power, and I must divide. Divide by, again, look at this. This is n plus 1. That means I should write minus gamma plus 1. Okay, I hope you understand, right? This n is like your minus gamma. Okay, and that is how this whole formula is written now. Okay, anyone has doubts, please ask me. Okay, but you have to go through. Okay, during our time also, we did not understand much, but we really have to go through these things. Okay, so you guys also. Okay, I think you're fine. Okay, so I also have to write the limits, right? I have to write the limits from v1 to v2. Now these limits, they will not enter just anywhere. Okay, they will only enter in the place of what? V. Don't think I'll come and replace gamma by v. Okay, no, gamma is not, v is not a value for gamma, right? V is a value for volume. So wherever you see volume, right, this upper and lower limits are going to enter there. The volume will enter in this v, and the upper volume v2 also will enter in that v. Okay, so let me just show you how it is written now. W is equal to, I'm writing K here, divided by, what is the denominator, guys?
Minus gamma plus 1.
Minus gamma plus 1. Okay, you'll agree I can write 1 minus gamma, right? Check this one. In place of gamma minus gamma plus 1, I can write 1 minus, same thing. Okay, no change. Then on this side, let me still write again this one, same thing. Okay, plus 1. I'm written the same thing, v1 and v2. Okay, I've written it separately because it has nothing to do with the values of v1 and v2, right? Because they will enter only here, right? Not in that power thing. Okay, so I'm going to now put the values. Check. Okay, W equals to, tell me, K1 minus gamma. In place of v, now what will I write, guys? V2 minus gamma plus 1. Then when I write the lower limit, right, when I put the lower limit, what should I write? Minus. Okay, then I write v1 minus gamma plus 1. Yes, okay, so this is what we have done. Not a problem again. Now there are a few more steps left. Okay, not very difficult, easy steps. Multiply this k with v2, multiply this k with v1 inside. Okay, so we'll do that. So help me out. What do I write? K times of v2 minus gamma plus 1 minus k times of v1 minus gamma plus 1 divided by 1 minus gamma. Okay, so this step, everybody, I think is clear. And there's one more thing waiting for us. Okay, what is that? P1 v1 to the power gamma is equal to how much? K. Even P2 v2 to the power gamma is equal to how much, guys? K. Okay, so in place of this k, look at this. This k, I'm going to use this one, and in place of this k, I'm going to use this one. Okay, because that will help us to simplify. Okay, so check. W equals to, waiting, in place of this k, what I told you I'm going to write? P2 v2 to the power gamma. Yes, then I'm going to write the other thing, that is v2 minus gamma plus 1. Okay, minus, what is this k, guys? Then this one, P1 v1 gamma v1 minus gamma plus 1. Okay, and then divided by again 1 minus gamma. Okay, now it is easy. Check. You'll agree with me that this is positive power. What is this? Negative power, right? So they will cancel. Or let me write in detail if you want. W equals to, tell me, what do I write? P2 v2, this is also v2, right? So what is the power, guys? This is gamma power minus gamma power plus 1. Okay, minus What is this? P1 V1 gamma minus gamma plus 1. I think you are clear, right? The bases are same, powers are added, no? This base and this base are same, this base and this base are same, so whatever powers they have, just add them, right? So that's what I've done. Say I've added the powers, okay, and obviously gamma cancel, this one cancels, okay. So we have a very simplified formula. Now tell me, work done equals to, tell me what is this? P2 V2 minus
P1
V1 divided by what? 1 minus
1 minus gamma.
Now you will also agree with me, right? What is P2 V2 equals to? Can I call it nRT or nRT2, right? And P1 V1 will be equal to how much?
nRT1
T1. Okay, I can use this because there are two different temperatures for P1 P2, okay, not an isothermal, so we can use them because yeah, they are what process? They are ideal gases, no? So I can use these two things there. Okay, so now waiting, guys, waiting for your help. How much should I write? W equals to N R T2 minus NR T1 divided by 1 minus gamma. So W will be equal to what now?
NR common.
Okay, NR common. Then I can write T2 minus T1 by 1 minus gamma. Okay, now you tell me which temperature is larger here for expansion? T1, huh? T1 is larger compared to T2. After expansion, the gas will cool, no?
Oh, yes,
so
sir.
this is lower temperature. So I don't want to write T2 minus T1. So what is the best way to write? T1 minus T2, larger minus smaller for expansion. Okay, so when I do this, when I reverse this, right, do you also agree I can also write here below, right? I can write gamma minus 1 or 1 minus gamma I can write?
Gamma minus.
Okay, I think you understand the step, right? Because I've changed the order of this, I can also change the order of numerator at the same time. Okay, so this is what I got. Okay, for 1 mole of a gas, how will I write, guys? W equals to, I'll simply write R. I'll write T1 minus T2 divided by gamma minus 1. Okay, so now properly you have to tell me. Okay, properly tell me what is this, guys?
Work done, total
Work done in expanding a gas.
Work done, okay, by the gas, not in expanding the gas. In expanding the gas or work done by the gas?
By the gas.
Work done by the gas when the gas undergoes expansion, right? When the gas undergoes expansion from volume V1 to volume V2, or let's say pressure P1 to P2, or let's say temperature T1 to T2, right? These are things changing, right? Under what conditions?
adiabatic
conditions. Okay, conditions, very good. Okay, now tell me, okay, so what does this work done depends upon? What do you think? If you can tell me, I'll be very happy. Look at this, I've given you a hint also. Does it depend on what?
Final temperature and initial temperature.
That's not the way to speak. Does it depend on initial and final? It depends on the difference in temperature between those two states or not.
Yes, sir.
If this difference is very, very large, okay, then automatically you are going to say what? It's not about initial and final. Okay, I know when you see T1 minus T2, like it looks like initial and final, but it's not about initial and final, but actually it's about the difference in the temperature between the two states. Okay, if a gas is really undergoing adiabatic expansion, okay, and it really has changed its temperature by a lot of amount, that means the gas has really done a lot of work. Okay, if the temperature changes very little, what do you think, guys? The gas has done a lot of work or very little work?
Little work.
Very little work. Yes, so Abhijit has understood. Okay, others also, I think you are clear, no? All of you? Yes, sir. All are clear.
Yes.
All are clear for today's class is
Yes,
clear, guys.
sir.
Today's class is clear for all of you.
Yes, sir.
Okay, so I'll tell you what kind of questions you're going to study. Okay, you are going to study, find the expression for work done during adiabatic expansion of a gas. Find the work done during isothermal expansion of a gas. That means the derivations. Okay, the numericals I'll do like this. I don't know your school has done or not, but I'll do like this. I'm still preparing some numericals. Okay, I'll send you that. Can you do it, guys, by yourself? But I will suggest you, okay, I'll suggest you, the first thing you should finish is the derivations, these two derivations. Anyhow, you have to do. Don't go to exam room without doing these two derivations, okay? I cannot say 100% it's going to come, okay? But, guys, did I share you Ambo's question papers?
No.
No, na? Okay. Jyotimoy? I shared with you Ambo's past previous question papers, no, not this present year. Okay, don't think I have a question paper of the present year. Okay, then
Yes, sir.
Jyotimoy, can you share it in the group again? The previous question
sir.
papers. You please check. All of you check. The Ambo's question paper is very very simple. Okay, but CBSE students though you have to study and all. Okay, everything. Okay, then Pringchi and all, no, they are from Paimon. Okay, so Pringchi and all whoever are from Paimon, you can share with me some questions, okay, which I can solve. Guys, we are meeting today's what day? Tuesday. No, we're meeting next Thursday. Thursday we will do 1, 2 and 3 topics, okay, because we need to do a bit more from Thursday onwards so that we finish. Okay, thank you. Jyotimoy has already sent. Okay, somebody please, Elishiba can also send. Elishiba is there. Oh, Elishiba disappeared. Elishiba is there. Elishiba is there. Elishiba, from this group, no, you send these questions to your own group also. Okay, you have their group, no.
So what questions?
But these are for Ambo students. Okay, so I do not know. I don't think so. You should. No need to read this right now. Okay, no. Jyotima is already sent in the group, but you can obviously check. These are the basic questions which you have to do. Okay, so yeah, you can send in your own group also, huh? From this group to you send to your own group. Okay, so I'll do like this. I'll send you some numericals quickly based on this. Then yeah, I think we are done for today, but next day onwards, okay, I really have to take some a bit longer. Okay, otherwise no, we will not be finishing properly. Okay, so bye. I'll not waste your time. Bye. Okay, thank you class.
Bye, sir. Sir, tomorrow at
Thank
3.
you.
Tomorrow at 3. Yes, we'll talk in the group. Okay, you just message me. Okay.
Okay, sir.
Okay.